Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Alright, before we move on to module number 8, which is deep generative modeling, I wanted to spend some time in the next couple of videos and talk about time series forecasting using deep learning models. During the course, in the previous video, we talked about how we can predict, for example, Apple's stock price using machine learning and econometric models. Now that we are familiar with basically deep sequence modelings like RNN, LSTM, we want to run a horse race between deep learning models, machine learning models, and econometric models. So so for this video, let's go over a Python folder that I created in module number 6. So if you go to lectures and code, go to deep sequence modeling, Python, and then this is the new folder that I created. It's called Univariate time series. So we're going to focus on predicting, again, the time series like stock market prices or returns using deep learning models. So there are 4 files in this folder. So basically the first one covers the univariate time series forecasting using prices. The second one using returns. And then we're going to compare the output of these things with what we already have from econometric and machine learning models. And this is the file that we're going to cover. Now, this is a notebook predicting stock returns using PyCaret. So we're going to use PyCaret package, Python package for that matter. And then finally, I'm going to go ahead and show you some plots when it comes to forecasting time series using 2 approaches. One using TensorFlow approach, which is not necessarily the most straightforward one, but I think because we covered everything in TensorFlow in this course, it's worth at least talking about it. However, I do it in more general way that it really doesn't matter if you do it in TensorFlow, PyTorch, you name it. You can use that one, which is available in this file. Okay, so without further ado, let's go ahead and open this one, univariate forecasting, and we're going to focus on Apple stock returns and talk about those predictions. Okay, so I already have all these things open at the top, and let me actually give you a preview of what we're going to talk about. So this is we're going to go ahead and prepare time series data for machine learning problems, specifically in this video, deep learning problems, right? We're going to talk about single output versus multi-output. So this is a question that some of you guys will also ask in my previous videos, that can we use machine learning models for multiple output predictions? And the answer is yes, absolutely yes. We know that deep learning models by construction can handle that. So if at the very last layer, you can go ahead and increase the number of neurons, and then you can have multiple outputs. In machine learning, it's not as straightforward as that, but it's definitely doable. Not all the machine learning models are able to do that, but some of them, like random forest or decision tree-based models, are perfectly capable of doing that. So we have 3 types of forecasting when it comes to time series. So this is a plot of log Apple stock price. So this is in log scale. And then we can have 1-step prediction. And this is our test set, right? So let's say from mid-August 2022 until December 2022, this is our test set, right? We want to do 1-step ahead forecast. So this is the orange line. The blue line is the actual log price. We can have multiple step ahead forecast, right? So this is that one. And then finally, we can have multiple output forecasts, right? Okay. So we're going to talk about all these things in the next couple of videos, but just be aware what you usually see when it comes to, for example, by the way, here I'm using LSTM and I'm going to show it to you. When you're using LSTM to predicting stock market prices or returns, usually people get excited by saying this one, say, okay, wait a second, we can go ahead and make tons of money, but that's not the case. Be careful. All these models that we're doing, as you can see, we're going to zoom in the video, and you'll see that these are all lagged. So it's not necessarily the best trading strategy, and we're going to talk about it. All right, so without further ado, let's go ahead and open these files. All right, I have all these files open here. This is our module number 6, univariate forecasting. We start with the returns and then the prices. And here's the actually predicting stock market returns, both price and returns using PyCaret package. So we're going to use it for simple econometric models and machine learning models. And then this is the fourth one, which is univariate forecasting TensorFlow approach for plotting the forecast, right? So actually, I think it's a good idea to start with this one, which is predicting stock returns PyCaret package to gives us some benchmark, right? What is the performance of the model, machine learning models and econometric models. So I have this one open here. I'm not going to run through the code actually. I'm going to simply walk you through the steps, right? So we have done a video on the details of stock market predictions using machine learning, and here's the YouTube video. You can click on it. Actually, let me go ahead and show it to you. So this one, it's a lengthy one. It's almost an hour. We talked about all the details about time series challenges when it comes to machine learning. So we said that how PyCaret is able to address some of them and not able to address a bunch of other the challenges of time series. Regardless, so here's the video. You can find the code and basically the explanation in the video. Again, going back to this notebook, well, actually, I think it's a good idea to talk about it, because I think in this one, by the time that I recorded this video, the PyCaret 3.0 was in the demo version. It was not completely released. You had to do pip install pre-PyCaret. Now you don't need to do that. So as of May 2023. You don't need to do pip install pre. So it used to be something like this, if you remember. So now we don't need to do that. So just go ahead and do pip install PyCaret. Make sure you use the full version because you want to get access to the XGBoost and more advanced models. If you do that, you should get PyCaret 3.0 installed on your computer on the Google Colab. Then let me actually show you the data, remind you what was the data set. We are downloading this data set, the CSV file that I have on my GitHub account. Basically, it's 5 years of daily stock data, and we're going to work with adjusted close for Apple's stock price between 2018 and 2022, end of 2022. It's 5 years of data, daily data. Then we already talked about sorting the index, fixing the indices, the time indices in this data set. And it's not a bad idea to quickly review that because I'm going to need it for today's lecture as well. So the index goes from the 2nd of January 2018 to the end of December 2022, right? So first things first, we need to make sure that these indices are the Pandas date time. So we're going to go ahead and change them to date time using Pandas library. And on top of that, we're going to make sure that the period is business days, right? So here's the indices. And if it is deep learning, that's enough. We can stop here. But if you want to use PyCaret package, you have to go ahead and do a couple of more steps, which is basically filling in all the missing values of the, let's say, the holidays in stock market, right? So actually, let me show you. This is the plot of adjusted close for Apple stock price. Then we're going to go ahead and make sure to fill those stock market holidays as well, like Thanksgivings and etc. Because this is just business days, goes from Monday to Friday, right? But sometimes and we need to make sure that the holidays are also taken care of, right? So, and we're going to go ahead and create our own index. The index goes from the minimum of data frame index to the maximum. So all the days are in between. So there are going to be 1304 days. And then we're going to say that, let me see actually. If you remember, the data frame that we downloaded has 1259, but there are 1304 days between those minimum and maximum dates. So it means that we're missing some days, right? So, and that's the goal. So first, let me show you what are those missing days. So by doing this symmetric difference, so if I do from this indices, give me the differences, both in either of the data sets, then there are going to be these are the dates that are missing in our data frame, right? And mostly they are, so if you look at that, it's basically Thanksgiving and the days that the market was closed. So I'm gonna go ahead, so remember we save it as IDX. I'm gonna go ahead and reindex the main data frame with IDX, and I'm gonna fill all the NA values with basically the missing values with NA, right? Now, if I show you the tail of the data set, it's something like this. So the December 26th of 2022, Thanksgiving now is an NA. We're gonna go ahead and forward fill this to make sure that we are using the last day of Apple adjusted close for this, right? So this is exactly how the stock data should be basically prepared, right? So we're gonna do fill forward. Now, if you look at the last 10 observations, now December 26 is gonna be 131.86, which is the closing price of the previous open market day, right? Which was December 23rd. So now we can pass this to our PyCaret. Without doing these steps, PyCaret is gonna complain. So just, you can give it a try and see what is the error message, but just be aware, this is a PyCaret thing, compatibility, we have to fix it. For neural networks, we don't care, honestly. But anyways, I'm gonna do it for the deep learning models as well, because we wanna make sure that this is apple-to-apple comparison when you wanna run a horse race between econometric model, machine learning model, and deep learning model. So I'm gonna do these steps quickly in all the notebooks. So here's our Apple stock price. Now we're ready to make predictions, right? So we're going to make predictions both for prices and returns, and we're going to use compare models from PyCaret and see which model is the winner. Okay, so creating our experiment, time series forecasting experiment, and basically the target is Apple, and we're going to predict one step ahead, right? So this is forecasting horizon. We're going to say use all the data in time windows, whatever that window size is, make a prediction for next day, right? And so this is our next day prediction. And don't worry about this. Do you need to do log transformation or not? PyCaret is automatically taking care of that part for you. Even if the dataset is non-stationary, when PyCaret is using machine learning models, it's going to use conditionally deseasonalize and detrend the data. So it's going to take care of that one. Again, I have talked about all these things in this video. Make sure that if this is something strange and new to you, make sure to check out this video first. All right, so then the experiment is set. We are going to go ahead and run compare models. Remember, these are the existing models in PyCaret and for time series. And we are going to compare those models, right? And I'm going to sort them by MAE because this is the metric, mean absolute error, that we're going to use for deep learning models. You can go ahead and look at the MAPE, mean absolute percentage error, but we can keep track of MAE just for the sake of simplicity. All right, so it seems that when we run this line, the winner between econometric and machine learning not tuned model is ARIMA. So ARIMA is powerful. This is nothing new. Usually when it comes to stock price prediction, ARIMA is one of the more powerful models. Can you make money with that? Well, the answer is no, but again, this is among the other models, this is the best. So we are looking at, for example, mean absolute error 2.19 or mean absolute percentage error of 1.7%, right? So maybe this is not a bad idea to remember this number. We're going to compare it with some other numbers from the deep learning models. The second one is simple decomposition, seasonality trend decomposition. And then, so our random forest model for machine learning is the next best. Remember, even though the data set was non-stationary, Apple price absolutely is non-stationary, the PyCaret is automatically taking care of that, right? It's going to work with conditionally deseasonalize and detrend the data. So if you look at the first difference, the data set is going to most probably become stationary. So don't worry about that one. So yeah, the winners are maybe ARIMA and then STLF, Random Forest, Cat Boost, and these are the boosting models which we already know that they're powerful. So for example, there's XGBoost. Yeah, XGBoost, surprisingly, they're down the list, but again, these are not tuned one, right? So XGBoost is here, Light GBM is here. So my guess is that if you tune these XGBoost and Light GBM, they're going to be among the top 10 performers or top 5 performers. And not surprisingly, again, the naive forecaster, which is what happens tomorrow, it's basically what was the close price today, right? So this is your simple random walk with no drift, so basically, right? And most of the time, that's among the top 10 or even top 5. This is not surprising at all, right? Stock market prices, we have market efficient hypothesis, and that means that basically it's hard to beat simple random walk with no drift, right? And that's the case. So this is a naive forecaster. All right, so this was the prediction for stock prices. We can, again, this is our winner model. We can go ahead and create the winner model, call it ARIMA, and then look what are the variables in the ARIMA. So it seems that these are basically AR1, and we have some seasonality with this seasonality of 9th, right? Which is kind of weird. So this is every 9 days, but anyways, this is what the data, what the model picked up, right? We can go ahead and finalize the model and make some predictions on the unseen data, right? These are the predictions going into the 2023, right? So we can change it to 2030, whatever. And we can go ahead and do some in-sample plots. Actually, I like this in-sample plots from PyCaret. It's not available for all the models, but for ARIMA, for a couple of other machine learning models, it's available. So we can do something like this. This is how the model is doing in-sample, right? I can zoom in and show it to you. And guys, this is pretty much standard when it comes to stock price predictions, right? So if you zoom out, you think that, wow, we are making tons of money if you basically use this model for prediction. Well, I'm going to show you the performance in the test set as well. It's nothing different. But remember, these are all lag indicators, right? If you zoom in, okay, maybe on average we're getting something, but these are not necessarily generating the best trading signals. So this is in sample. We can go ahead and look at the forecast, right? So this is our forecast into 2023. And was it like this? I don't know. We need to check it out. Okay. So, and these are the confidence intervals. So that was the prices. Let's quickly look at the returns. So nothing new here. I'm going to go ahead and manually create our log returns, which if you have a little bit of background in finance, you know that if I go ahead and calculate the log price and then look at the difference of that log price, this is simply my these are my returns, log returns, right? So diff log apple, this is simply your log return. If I take, for example, this price divided by this price and subtract 1, roughly it is going to be this percentage. Okay. So then I'm going to pass this log return to my experiment number 1. So remember, the experiment EXP we reserved it for predicting stock price. EXP1 is for basically log returns. Same stuff. We're going to look at basically all the models. I'm excluding auto ARIMA because it's going to take some time. No, especially if you're doing it on your local computer, maybe it's not the best way to do that. But anyways, if you have time or more powerful machines, or you want to run it on Google Colab, you can definitely let that include the auto ARIMA as well. Regardless, for returns, it seems that, again, these are not tuned models. If you tune them, the ordering might change, right? For returns, it seems that, again, the econometric STLF, simple decomposition, seasonality trend decomposition is the winner with the MAE of 0.018, right? So this is the number that we want to compare with the deep learning models. The machine learning models are next, Light GBM, CatBoost, XGBoost. So these are all among the better performers. And look at this, SNAIVE. The SNAIVE, it's basically, this is your seasonal naive forecaster. Your random walk with no drift and adding seasonality. And you see this is among the top 5 performers here. Nothing surprising here. When it comes to stock price, that's always the case. This is stock return. We have this seasonality as well. Okay, so yeah, where is our ARIMA here? I'm curious. So ETS is here. We excluded auto ARIMA, but ARIMA, it seems that the ARIMA itself was also taking long, so it automatically dropped. There's this cutoff here that if some of those models is taking longer than the cutoff, it's going to be excluded from the output. You can change those settings in PyCaret. All right, so oh, I see. I manually created ARIMA here. I just was curious to what is the performance. So again, performance of MAE 0.0206. So the winner was 0.018. So let's take this one as a benchmark, or something like that, 0.02 as a benchmark from the econometric and machine learning models for predicting stock market returns, and see how basically the deep learning models is able to compete with that. Okay, so remember that number, 0.02. And here are just some plots for return predictions. Again, nothing fancy here. These are the blue line is the log return, and the orange one is what the model predicts, right? You can look at some predictions out of unseen data into the future. So we are looking at maybe the first couple of months of, what is it, 30? Yeah, a month and 10 days. You know, these are trading days, remember, into 2023. All right, so this is a quick review of predicting stock returns and prices using PyCaret with econometric and machine learning models. Now let's look into the deep learning. Let me actually reconnect. Hopefully I don't, yeah. Let's see. Okay, so I have to go ahead and run this Colab one more time because it's been a while I didn't check it out. So let's go ahead and run it all. I'm gonna pause the video and then come back when it's run. So this is gonna take, I don't know, about 10 to 15 minutes to compile because we have a bunch of deep learning models. We're talking about simple RNN, LSTM. We will look into stacked RNN and bidirectional RNN. So this is gonna take 10 to 15 minutes. So I'm gonna pause the video and come back. Okay, so the models have been run, and then now let's look into the details. So again, the first part is going to be pretty much the same as what we did in the predicting stock returns, PyCaret notebook. So I'm going to skip through them and then directly go to the rest of them. So, yep, there you go. This is a data set. We're going to go ahead and change the index to time index and then into period, and make sure that we are, again, adding the NA values with field forward. So here, this is our December 26th, Thanksgiving of 2022, filled with the previous number. So pretty much the same stuff, right? So, and then we're going to go ahead and create the log prices and the log returns. So these are the log returns. Obviously, it's a stationary. The variance is changing, but let's say we take it, it's a stationary, right? And then we can go ahead and use our deep learning models to these stationary log returns, right? So here's the data frame, the F. We're gonna twist this data frame a lot, so let's keep track of all the columns and everything. So as of now, we have price, log price, and log return. So diff log apple. This is basically your log return. Okay. So usually we normalize the data. Here we don't need to because the data is already, we want to work with this ones, right? It's already basically stationary. We can go ahead and do that. It doesn't hurt. But for example, if down the road in this notebook, when I talk about the log returns, I'm going to go ahead and normalize them. So if you want to normalize them, make sure that you're not cheating. It means that you have to use a train set to figure out what is the average and variance, the parameters of interest, and then apply those numbers to the test set, right? So that's why we have to say, take all the observations from the train set, take the average, and then this is your average, demean the data. So this is subtracting the mean. Let's call it demeaning the data. And then calculate the standard deviation, divide everything by standard deviation. So this is your normalized data. Okay, here I'm gonna skip it, but in the next notebook we're gonna do that. All right, so let's go ahead and split the data. So the length of the data frame is 1304. Well, actually, I wish I didn't do that. We are gonna go ahead and change it to some other numbers. So don't worry about it. So I'm not gonna run these cells. I'm gonna just walk you through because it's gonna mess up with these numbers. So our train sample, let's say 60% of the data trained, 20% is going to be validation set, and let's say the rest is test set. Remember, this is deep learning, so we need a relatively large validation set, and of course larger train set, and everything else we can put it in the test set. So let's say we have 782 observations for train, 260 for validation, 262 for test, right? Then we're going to use this time series batch generator from TensorFlow. We have seen this before, right? So let me actually walk you through when you saw this. If you go back one folder in the Python, when we talked about this deep sequence modeling RNN LSTM, this was a multivariate forecast. We actually forecasted a temperature based on 14 or 13 other features, if I remember correctly. But there we talked about this time series batch generator, which is available in TensorFlow. So I'm going to go ahead and quickly review it one more time. All right, so here's the documentation for that time series batch generator, but I'm going to quickly walk you through what is it. So for example, first of all, remember these things. This is our number of train samples, number of validation samples, number of test samples, and I'm going to go ahead and use this time series dataset from array, utility from keras.utils, right? So what does it do? Let me actually run it once and then walk you through how we can play around with this. So we are importing NumPy TensorFlow from TensorFlow keras. Let's say we have an integer sequence of bit 0 to 12, right? Not including 13. So this is my time series, 0 to 12. These are some indices, right? Or integers. Batch size. So let me actually show you. This is time series data from array. There are some, let me actually open the documentation. Maybe this is easier. So here's the documentation from TensorFlow, right? So time series data set from array. We have to pass data, target, sequence length, sequence stride, sampling rate, batch size, shuffle, and seed number, and start and end index, right? So these are the inputs. Let's define them one by one. So batch size, for now I'm going to use 1. So if I use 1 batch size, it means that at the end of the day, so for example, this is one batch, this is another batch, this is another batch, and etc. Right? So this is your batch size. Number of time series samples in each batch, right? Then the next one is sequence length. This is the length of the output sequence, basically the number of time steps. So for example, if I set it to 5, I'm going to say sequence length of 5, right? So 5 here, 5 here, 5 here, etc. I can go ahead and change the batch size to see what will happen. If I change the batch size to 2, you'll get something like this. So batch 1 has 2 time series in it now. So sequence length 5. I can go ahead and change it to 3, and obviously, surprise, surprise, you're going to have in each batch, we're going to have 3 time series, right? So let's keep it to 1. And then another thing that I did, actually, this is what I'm going to add to the code. This is not in TensorFlow, but I'm gonna make it consistent with time series language, right? So in time series language, we have this forecasting horizon. So I call it h is equal to 1. This is a number of h steps ahead for forecasting. So it means that if h is equal to 1, says use the past 5 numbers and make a prediction. Your target label is going to be the next one, right? So let's run this. So what does it mean? 0, 1, 2, 3, 4. My target is going to be number 5. 2, 3, 4, 5, 6. The target is going to be number 7. Does it make sense? If I go ahead and change this h to 2, I'm going to make 2-step ahead predictions, right? So for example, 0, 1, 2, 3, 4. So the target is going to be not 5, but 6. So in 2 time steps. So this is a forecasting horizon. In the next, I can say, give me the prediction in the next 4, whatever. If it is days, let's 4 days, right? If it is hours, 4 hours. So 0, 1, 2, 3, 4. So I have to skip 3 and then go to the 8. So this is the prediction in the next 4 hours or days, right? So that's what this h is doing. And how we incorporate this h to the time series data from array. So we have to go ahead and define our delay. So the delay is simply the sequence length. Imagine here is 5 plus h minus 1. H is your forecasting horizon. Basically, it says that wait until the time arrives for making prediction, right? So if H is equal to 1, basically sequence length. So 5, so the delay, basically here says that your integer sequence go from the beginning to the last 5 numbers, and then make predictions from that last 5 number all the way to the end. Hopefully that makes sense, right? Try to write it on a piece of paper or just code it from scratch. It should make sense. So this is your data. All these numbers, again, from the first index to all the way, because we don't want to go out of bounds, right? So that's why we have to exclude these. These are going to be your targets, right? The target is going to be from this delay all the way to the end. Sequence length is your 5. Sequence stride. Oh, we didn't talk about a stride. So a stride is a number of time steps between 2 consecutive output sequences, right? So I can go ahead and change, and then it's easier to see it that way. If I change it to 2, right? So what will happen? Then now I have 0, 1, 2, 3, 4, and then 5. Let's see, actually. Yeah. And 5 is the target, so the sequence stride is 2, means that the next target, the difference is going to be 2, so 7, and that's going to be the case for all the inputs as well. So 0 goes to 2, 1 to 3, 2 to 4. Let's go ahead and change it to 3 if it was out of range. Yeah, so 0 and then 3, 1, 4, 2, 5. So here the target is 5 and the next one is 8, right? So this is what the stride is going to do. We're going to keep it to 1, and then shuffle here is equal to false. I can go ahead and turn the shuffle to true. Remember, shuffle is not shuffling time series. It's shuffling the time series in each batch, right? Here we only have one batch. So if you want to see what shuffle does, I need to go ahead and change this to true, and obviously add another batch, maybe 2. There you go. So look at that. The time series in each shuffle is in each batch is not shuffled. The time series themselves, so for example, this is one time series, go 3, 4, 5, 6, 7. No shuffling here. But between time series, we are shuffling, right? So the first one is 3, 4, 5. The second one is 2, 3, 4. If I can add the third, maybe something like this. Now you get the idea, right? So if I don't shuffle, if I put the shuffle is equal to false, it's going to start from 0, right? 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, right? If I change the shuffle is equal to true, it's going to go ahead and shuffle these time series, right? Between time series, it's going to make the shuffle. Within time series, obviously, it's not going to shuffle because it doesn't make any sense. This is time series. All right, so now that we know how this time series dataset from array works, let's apply it to our data frame, right? Remember, the data frame has a column log returns or diff log apple that we want to work with that, okay? So yeah, this is where I'm going to define the series. This is my data. This is the data that I want to play around with, make validation set, test set, and train set out of it. And yeah, I'm going to go ahead, because the first one was NA, I'm going to drop that one and then change it to NumPy array. And yeah, these are the log returns. So let's use sequence length 60. This means that we're going to use the past 60 observations, here days, to predict the next day, right? Next day, H is equal to 1. Forecasting horizon is equal to 1. Everything else is pretty much the same. So except that, again, this is deep learning. We want to train a model in different batches, and that's why we say batch size is equal to 32, and etc. So we're going to run this time series data set from array 3 times, 1 for train set, 1 for validation set, 1 for test set, okay? And I'm doing nothing fancy here. This is exactly what we did above, right? This is exactly the same thing with the new, of course, parameters. Okay, and I keep the shuffle is equal to false. Yeah, if you run this, then we have a data set, which is a TensorFlow type data set, right? And this means that in each of those data sets, it's a tuple. You can unpack that tuple. The first argument is inputs. The second one are the targets. Take one means that give me the first batch, and I can print them out, right? So this is time series. For example, this is my input, and then here are the outputs, right? So I'm going to have 32 of these predictions. You know, these are one-time step ahead predictions, right? And these are, so for example, this is going from day 0, which I believe was the 2nd of January 2018, and so 3rd, 4th, 5th, and etc. And we're going to make a prediction. If you use 60 days, we make a prediction for the 61st day, which is this number, right? All right, so now what is the shape of this input and target? Obviously, for the input, we have 32 batches, and each of them have 60 observations. For the output, we have 32 batches. Obviously, for each of them, there's one prediction. So it means that they're going to have 32 numbers. That's it. Okay. So what is our baseline or benchmark? Again, we have done this before. So we did it here in the RNN LSTM for multivariate time series. Now we do it for here, pretty much the same stuff, right? So I'm going to go ahead and define our evaluate naive method. And maybe this is not the best name here because naive forecaster in time series has a, well, actually, yeah, sorry, my bad. This is good. This is your random walk with no drift. And basically it means that whatever happens today is the best predictor for tomorrow, right? Again, nothing fancy here. We're going to go ahead and calculate the mean absolute error. And as you can see, it says that the predictions are the last observations in the samples, right? And the samples are the input from the data set. So the last observations, we are going to use it for prediction for tomorrow. We're going to add them up and then divide it by the number of samples seen. So this is your mean absolute error. If we run this for the validation, MAE is going to be 0.015. For test, MAE is 0.026. So this number should be comparable to what we had in PyCaret. So let's go back here. We did the returns. So for PyCaret, what we got was, yep, this is S naive. For our naive forecaster was this, yep, this one. This is what we're doing there, right? 0.03, what we get here, 0.026. Well, obviously they are not exactly the same because the number of train and test observation that we used was slightly different, but again, that's the idea. But I think, yeah, this is our benchmark for the deep learning model. But again, we know that from econometric and machine learning, the number that we should aim for is something like this, 0.018. Let's see if the deep learning model can beat this number, 0.018. All right, let me close out this one. All right, so I'm gonna create a dictionary, call it test performance, and add this first one. This is my baseline to that dictionary, right? So we're going to go ahead and add a bunch of other models to that. So here we are in common sense or baseline. Then we're going to do simple RNN, LSTM, stacked RNN, bidirectional RNN, and finally compare those models, right? So simple RNN, and we have done this before multiple times. Now you know the details. It should be easier to follow through the code, right? Just a reminder, the sequence length is 60. Number of features here is 1 because we have a univariate time series prediction. And we're going to go ahead and define our regular simple RNN architecture here. The inputs are going to be, the shape is important. It's 60 by 1, right? And then we're going to add the first layer, which is a simple recurrent neural network with 16 recurrent cells. Why 16? Again, there's no magic number. You can try 32, you can try 64, and but whatever it is, make sure that it's not bigger than the sequence length, you know, to avoid that bottlenecking problem. So 16, we're gonna go with 16, and the output layer is just one simple dense layer with 1 neurons because there's 1 output, right? So it is important. We're going to use 1 because it's 1 output. We make predictions for 1 step ahead. Let me actually remind you what I'm talking about here. Oopsie, not this one. Okay, so remember, we can use these time series forecasting models in 3 fashions, right? So one is 1 step ahead predictions, which is using single output model. One is multiple step ahead predictions, which is again using single output, or multi-output predictions, right? So we're going to talk about the differences. So I have some tables, so hopefully it makes sense if you see the tables first and then follow along the code, right? So this is our single output. What we're doing, when I'm doing something like this is the single output because the dense number of nodes is equal to 1, so it's going to generate one output. So let's go back to this one. Means that, so for example, here's your input features, right? And this is your single output. So this is today, yesterday, the day before yesterday, and etc. So this is today, lag 1, lag 2, lag 3. I have 4 observations, and I'm going to make a predictions for tomorrow, which is, let's call it forecast h is equal to 1 or lead 1. So this is y5. Then next one, I have 4 other observations, make a predictions for the day after that, right? So hopefully this makes sense, right? So at the end of the day, I have 10 observations, and then I have 10 rows, right? And then 10 predictions. So this is single output, right? Okay, so what we're doing is that single output thing. Okay, so a quick reminder, how do we get the parameters of the RNN model? Remember, these are recurrent cells. So it means that because I have one feature, we have 1 multiply 16 cells, right? And then we have 16 squared or 16 by 16 hidden state weight, right? So these are recurrent cells. And then we need to add 16 bias terms. So if you do the math, you get 288, right? For LSTM, you need to multiply this number by 4 simply because we have 4 gates. All right, so callbacks, let's save the best model as RNN, and then the metric is going to be MAE. We're going to keep track of that. You can run it for more epochs, but again, the data set is small. Usually we don't get a good convergence here, but anyways, you get the idea. This is at the high level what we're doing, right? When it comes to deep learning models, of course we need more data, but here we only have, I think, 700-ish for train and 200-ish for validation. We'll see how the model is able to do that. It's not doing a bad job, by the way, even with this relatively small size of data. Okay, so the model has been trained. We can look at the performance of the model in the test set, which is 0.01774 right up the bat. It's not bad, right? Remember, this was our best performer, relatively, quote unquote, in econometric and machine learning. We already beat that one with a simple RNN, which is not bad, right? So we're going to go ahead and save it in our test performance dictionary. So now in the dictionary, we have baseline, we have simple RNN. Okay, we want to see, basically look at the MAE in the train and validation set versus the basically epochs, right? And it seems that the validation, again, right away, the performance of the model in validation is better than train. What does it imply? It implies that the model, well, the train set was small, so that's one thing, and the model didn't learn that much in the train set and got lucky in the validation set, something like that, right? So this basically suggests we need a more complex model. The bias of this model is high. We need to do something about it, right? So one way to think about it or make it more complicated is just do LSTM, right? We're going to go ahead and do LSTM. Same architecture, simply just replace the simple RNN to LSTM. And number of parameters is going to be multiplied by 4. So that 288 is going to be multiplied by 4 here. So that's where we get this number of parameters here. All right, again, save the best one as LSTM. Same metric. Optimizer add-up. You can go ahead and change it to RMS prop, but again, it's a matter of try and error. And then let's see, what is the performance? The performance in the test set is 0.1715. Okay, so now if you want to compare the three, we have 0.25 for baseline, 0.1773 for simple RNN, 0.1715 for LSTM. So LSTM is already better than simple RNN. Not that much better, but it's slightly better. Okay, again, if you look at the validation and trained mean absolute error performance versus, this should be the loss, right? These should, let me see. Well, actually, yeah, we're plotting the MAEs. We could have plotted the losses as well. Well, I don't want to run it again because the model history is something else, but you can plot it for losses and it tells you a better story. Okay, so then our next job is to make the model even more complex, right? Let's see if we can do that. So I'm going to stack a bunch of RNN and LSTM layers on top of each other to just give it enough complexity in a way that the performance in the trained set should be usually better than validation set, right? Not the other way around. Let's see if we can get that. So again, the input shape is 60 by 1. And then the first LSTM, let's do 128 recurrent cells. I'm going to use recurrent dropout of 10%. And remember, because you want to stack a bunch of recurrent cells on top of each other, you have to do return sequence is equal to true for any intermediary layers, right? So if I had another recurrent layer here, I had to go ahead and switch this return sequence is equal to true for this layer as well. But here we don't have any other recurrent layer, so we're going to go ahead and switch it to false, which is the default thing. All right, so I have LSTM. On top of that, I have a simple RNN with 128 cells. And then I'm going to go ahead and add a general dropout for regularization. Again, you can twist this deep neural network architecture as whatever way you wish. It really doesn't matter. It's more of an art rather than science. You can try and error and see which one works best. We talked about all these architecture designs as well, by the way, at the beginning of the course. And all right, so we are going to go ahead and save the best one as a stacked regularized. And this is regularized and stacked, right? A couple of layers. And then let's see how it performs. So after 20 epochs, this is what I was talking about, right? So usually if the model is complex enough, the trained set performance should be not worse than validation set, right? And we're getting there. We're getting there. Again, the reason is that this is not quite there is their sample size is quite small, right? So let's look at the performance in the test set. Let's save it in our dictionary, and these are the performance, right? We are doing better. So this is 0.01697. So it's better than the LSTM. So we're doing relatively better, right? So lastly, we want to do bidirectional RNN and see how it performs, right? Usually when it comes to stock price, I don't do that. I don't even bother trying that, because if I get a better performance, that should be chance or some weird, I don't know, randomness. Because stock price time series, the bidirectional makes sense if you are dealing with time series like text, right? You can go from left to right chronologically or anti-chronologically, and it still makes sense and you can read stuff, right? But for prices, that's not the case. But regardless, just for the sake of completeness, I'm gonna do it. So we're gonna add this bidirectional layer, and inside that bidirectional, you can use anything. You can use a stack, you can use LSTM, you name it. You can do whatever you want. I'm using a simple RNN. And then on top of it, a dense layer with single output. So again, we talked about single output there. And yeah, let's see how the model performs. So scroll down. This is how the model performs in the test set using the bidirectional RNN. Again, not surprisingly, it cannot outbid even the simple RNN, right? This is our simple RNN. This is our bidirectional simple RNN. So yeah. So the winner is going to be our stacked RNN. We can plot it, right? So we can go ahead and make a plot. This is a simple plot, because remember, our test performance is a dictionary. I can grab the keys, I can grab the values. So these are the models and values. And then I can do a simple bar plot, right? So here's our simple bar plot. LSTM is powerful. And then stacked RNN is slightly better than that. But for the rest of this notebook, I'm going to stick to LSTM to keep it simple. And I'm going to use it for making some plots, doing one step ahead, multiple step ahead, and then multiple output predictions, okay? All right, so let me go ahead and stop it here because the next one is going to be a new video. I don't want to make this video super long. So what we did so far, we use PyCaret to run a horse race between econometric models and machine learning models. The winner for the returns was a combination. They're all good. Your econometric and machine learning, the performance are relatively the same, right? Then we tried deep learning models, and it seems that LSTM and stacked RNN are doing a good job. And by the way, I'm not covering the transformers yet because again, when it comes to stock price, it doesn't make a big improvement. So usually our stacked RNN is still the winner, especially for the returns. But you can go ahead and give it a try. We talked about transformers, how to code transformers from scratch last time. When it comes to time series, you can use a package called Dart, specifically for time series. Darts, D-A-R-T-S. And then there you can use a TFT model, temporal, let's see, temporal fusion transformers for time series prediction, right? So Dart's package makes your life a lot easier if you want to use basically transformers for time series prediction. I'm not going to do it here. Later in the summer, I may do that, when I'm developing the deep forecasting course and publish it on YouTube. But for now, for time being, we're going to stick to traditional machine learning, deep learning models, which, by the way, they performs mostly better than transformers when it comes to time series. All right. So, and one last thing I just wanted to tell before going to the next video is that what we're doing is single output prediction, right? So what your deep learning model was basically calculating is the difference between the blue line, these are the log returns, and the orange line, one step ahead forecast. So what we did in econometric, what we did in the machine learning, what we did in deep learning is basically that number 0.017 or 0.018 mean absolute error is this. It's calculating the difference between these two. We're using one step ahead predictions, right? And so that means that once you're here, you make a prediction for tomorrow. Then use that, then you wait 1 day. Now you have the information for tomorrow, then use the past 4 days to make a prediction for the other day, right? So it means that we are building these forecasts on top of each other chronologically. So when I'm here, I wait 1 more day to get the data, run the model again, same window, using the past 60 days to make a prediction. So this is what we're doing. And we're going to report that number in the entire test set. So this is my test set, this is my train set. Hopefully that makes sense. So in the next video, I'll talk about, let's say, how can we do multiple step predictions or multiple output predictions. Okay. Until the next one, take care.